ways through mechanical means, biological means, and chemical means. So I know y'all are really interested in chemistry, and we'll talk more about that in a few minutes, but we need to talk about the other things that we use to clean the wastewater up. So what does raw wastewater look like? Well, you can only imagine. This is just a sample that my operator pulled, and that's kind of that's representative of what the raw wastewater looks like coming into the plant. It's organic material. It's got nutrients in it. It has ammonia, phosphorus. It has a BOD. I think I heard Jay mention BOD. Did anybody know what BOD stands for? Y'all gotta know this one. BOD.
Crap.
This is going to be on your test. I'm just kidding. Biochemical oxygen demand. What does that mean? BOD. That's the amount of oxygen that's going to be required to stabilize the organic material in this raw wastewater. Okay? So this is going to exert an oxygen demand for treatment. Whether it go into our treatment plant or if it went into a river, lake, or stream, it's going to exert an oxygen demand. So if it went into the river, it's going to consume all the oxygen out of the water. There's oxygen in the water. There's DO. There's all the oxygen in there for the fish and that sort of thing. So if you take all that oxygen away, the fish are going to die. All the organisms in that stream are going to die. And kind of what Jay was talking about in there, that's called eutrophication. You can kill a river, lake, or stream with too much BOD being introduced into it. So that's what raw wastewater looks like. It's got all kinds of nasty stuff in there, obviously. We're going to screen this raw wastewater out. We're going to screen it. We're going to degrid it. And you're looking at me like, what in the world are you talking about? But once you get out on the plant, you're going to see what screening is. You're going to see what grit removal is. But we're going to screen this raw wastewater. We're going to degrid it, and then we're going to introduce it into a biological process. Biological processes are what we use to clean this organic material up that's in the raw wastewater. It's a food source for microorganisms. They're going to feed on this. So as long as we have microorganisms to do that, we're going to be in pretty good shape. So how do we grow microbes? Where do we store them at? We have a process that we call activated sludge. And we store that activated sludge in what we call our BRB basins, biological reactive basins. Each one of those basins can store up to about approximately 3 million gallons of activated sludge. So right now we got 3 basins in service, so that means we can store about 9 million gallons of activated sludge in those 3 basins. Okay? So we're building a mass of organisms that will consume this continuous flow of organic material that's flowing into the plant. Because remember what I said, we got 14 million gallons of wastewater that's continuously flowing into this plant. We've got to have plenty of microbes to break down and consume this organic material. What are microbes? I'm sure y'all know. Amoebas, crawling ciliates, stalk ciliates, rotifers, water bears. There's a whole array of microbes that we use to break down this raw wastewater. And if you look up here, you'll see just a list of some of the microbes that do the work of breaking down that organic material and breaking down and consuming the BOD that's in that raw wastewater. Those microbes also break down ammonia and phosphorus. The ammonia concentration coming into the plant is probably 20 milligrams per liter ammonia. You can't discharge that into a river, lake, or stream because, like Jay said in there, it will cause algae blooms. It'll make algae grow. It'll consume oxygen. So we want to break down that ammonia. How do we do that? We got microbes that we grow out there in the basins in the biological process. There's 2 of them. There's Nitrous amonis, Nitrobacter. The Nitrous amonis will convert ammonia to nitrite. The Nitrobacter will convert nitrite to nitrate. Then we run the whole system in the biological process through a denitrification process where nitrate is converted to what? Anybody know? I just thought y'all might know some of it. Y'all know what ammonia? Chemistry, ammonia, right?
Mm-hmm.
What you can break it down, right? Nitrite, nitrate. What's the simplest form after that? After it's broken.
Nitrogen. Nitrogen monoxide.
No. Well,
Just straight
it breaks it
nitrogen.
down into nitrogen gas. The nitrogen gas is released into. So you go from NH3 to NO2 to NO3 to N2. Am I right? I get confused sometimes. But so some of these microbes, we call them autotrophic. I may be saying that wrong. Autotrophic bacteria that convert that, and that's the Nitrosomonas and Nitrobacteria that do that for us. But we got to grow them. They're very sensitive to a lot of things that come down the pipe to the wastewater treatment plant. So we got to be careful on what's coming in, because those nitrifying bacteria are really, really sensitive to temperature, pH, dissolved, the amount of DO in the wastewater. They're very sensitive to certain things. So we got to keep those microbes happy. We got to make sure we don't kill them off, because then nitrification is not going to occur. The other thing is phosphorus removal. We got to remove phosphorus as well. It's a nutrient. It causes things to grow out there in the rivers, lakes, and streams, so we want to minimize that before we send the wastewater on its way after we treat it. So how do we do that? We got two ways of removing phosphorus. It comes into the plant around 7 to 10 milligrams per liter, okay, in that raw wastewater. But as it goes through the biological process and it's being treated, there's bacteria, microbes in there that convert phosphorus. They don't convert phosphorus. They actually they take phosphorus into their cell wall, absorb the phosphorus. And how do we remove the phosphorus? Well, eventually we're going to take some of those solid materials and we're going to waste them out of the system. We're going to remove them from the process. And that's how you really get rid of phosphorus. We could also remove phosphorus through chemical treatment. And we can add a chemical called ferric sulfate. Anybody know what ferric sulfate is?
That'd be iron sulfate, wouldn't it?
That's exactly right. We use ferric sulfate, which has a pH of around 2, and we use it to precipitate out phosphorus in our secondary clarifiers. So what we're doing is we're taking soluble phosphorus and converting it into insoluble phosphorus, precipitating it out into the clarifier, it settles down, and then when we waste that solid material off the bottom of the clarifier, that solid material, that's how net phosphorus removal is achieved. Okay, but we got to bring the BOD down, the total suspended solids, ammonia and phosphorus, down to a certain limit when it leaves the plant, because we have a permit that we have to comply with that's issued from the Environmental Protection Division of the state of Georgia. So they say you got to meet these parameters before you discharge that water. So we got to, make sure we meet those limits, which there's limits for phosphorus, BOD, total suspended solids, pH. There's a whole wide array of permit limits that we have to achieve before we can discharge that water. So one thing we really want to show you, you can't see microbes. You have to be able to look at them through a microscope. You can't see them with the naked eye. So we got this up here on the computer screen, and you see that microbe. You see how he's going in there and he's eating food. He's eating organics in that raw wastewater. That's a rotifer right there. But it's pretty cool to watch him in action. But without him, the biological process wouldn't occur, and we wouldn't get that BOD removal. We wouldn't get that ammonia and phosphorus removal unless you added a bunch of chemicals. Now there are different ways to remove that stuff. There's filtration, there is chemical treatment, but when you start using like chemical treatment for those types of processes, it can get very, very expensive. So if you can do it through biology, that's the best way to do. These microbes do the work for us. The only thing we have to do is feed them, just like you and me. They need food. What's their food source? The raw wastewater. We got to supply them with oxygen too, because if they don't have air, they're not going to survive. They're going to die. So we blow air into the activated sludge process to give them air to breathe and to keep things mixed up. So, but you'll get to see the biological process, and you can ask more questions when we get out there. All right, here's where y'all come in. Chemical treatment. What do we do with chemicals here at this plant? All right, one chemical that we use every single day, 24/7, 365 days a year, we have to meet a fecal coliform limit, permit limit from EPD, which was what Jay was talking about in there. He runs those fecal coliform tests for us. So we have to feed sodium hypochlorite, 12.5% sodium hypochlorite, to our plant effluent. And we do that for disinfection, to kill pathogens. Okay? So we're always feeding the sodium hypochlorite into the water as it leaves the plant. We also, like I said before, we use the ferric sulfate to precipitate out phosphorus in the secondary clarification process. We also use sodium hydroxide. We don't use, let me back up a little bit for a minute. We don't use the ferric sulfate all the time. We only use it as needed. Because if the biological system is working like it's supposed to, we don't have to feed ferric sulfate. But if it gets out of balance, or if the phosphorus limit edges up a little higher than we would like it, we start up ferric feed to knock that phosphorus down. But you remember I said the ferric has a real low pH. You start feeding that into a biological process, it's going to destroy alkalinity. Your pH is going to start dropping. Those microbes are sensitive to changes in pH, and they don't like it. So you could actually kill off some of your microbes, or all of them, if you allow that pH to drop too low. But you're having to feed that ferric sulfate into the system to meet that permit limit on phosphorus. So what can you do? What can you do? You add the sodium hydroxide back into the process, because sodium hydroxide, what we use, has a pH of around, anybody got an idea?
It's pretty high.
Huh?
My guess is 9.
It's 13 or 14. So it's great for putting the alkalinity back into the process. It's alkalinity being your buffering capacity to prevent your pH from dropping out. So as long as you got alkalinity, your pH is not going to start dropping. So my operators are constantly collecting samples, running tests. They monitor the alkalinity. They see the pH. If they see that starting to drop, especially if we're feeding ferric, they really watch it real close. If they start seeing the alkalinity drop off in the plant effluent, they'll start up the sodium hydroxide to add some alkalinity back into the process. So those are the 3 chemicals we use here at the Casey plant to treat wastewater. I also want to just mention to you that when the water leaves here, we're not finished treating it yet. It goes down to our constructed wetland site. Has anybody ever heard of our constructed wetlands here at the Clayton County Water Authority?
Is that Rough and Dark Road?
Yes.
Yes. I lived across from it.
Right. Well, what you may used to have seen was the land application system. We've actually converted the majority of that over to constructed wetlands. So what happens is, as the flow leaves here, and it's highly treated, it looks good, and it meets all the permit limits, but it goes to the constructed wetlands, where it moves through these series of cells, these wetlands, and that wetland acts as a natural filter. All the vegetation in there uptakes phosphorus, ammonia, BOD. So as the water finally moves all through that natural process and it gets to the end, and it actually is discharged into our reservoirs here in the county, it's very, very clean water. So it's a nice and natural cycle of water. Another thing I wanted to mention as well, Mike, do you know where the pellets went? Are they right in front of me? Oh, there they are. Put them up here. I think some of this will start coming to you a little more once we're out there on the plant and you actually can lay eyes on some stuff. But this is what your activated sludge looks like. That's what it actually looks like. Okay? And you can see there's a lot of solids in there, right?
Yes.
It's got to be removed. Really, that's not a bunch of this. It's really not. There's some of this in here, but mainly this is microbes feeding on that. So these microbes in this activated sludge process are eating that. So you can imagine this is a living organism, right? So if you allow this to grow and grow and grow, what happens? There's not enough food in here. Yeah, there's not enough there's not enough food in the raw wastewater because you got too much activated sludge, too many microbes. So what happens? They don't like that at all. They start starving, just like you and me. If there's not enough food to go around, you starve. They start cannibalizing each other. They go into a process called endogenous respiration. So they start cannibalizing each other, and it's not good for the treatment process. You don't want that to happen. So what do? You have to take some of those solids out of the system, or those microbes. You waste them out. What do you do with them? Well, here at the Casey's plant, we turn them into fertilizer. We got a pelletizing facility that takes the microbes and the solids, turns it into a pelletized product, and we sell it to a broker, and they put it out on farmlands throughout the southeast, all over the place. We sell every bit of it that we produce to that broker, though, and it's registered with the state of Georgia as a fertilizer. It's called AgriPlus 650. 650 being the nutrient ratio. So, another thing to consider too, you can let this grow too much, like I just mentioned, where it gets out of balance, and you got too many microbes and not enough food, but it can go the other way. You can waste too much of your microbes out of your system if you're not careful, and it's been known to happen at other places, but if you're not watching the system, if you're not watching it, if you're not watching it very closely, you can waste too much of that out. Then what happens? Then you have too much food and not enough microbes, so you get a bleed through, so to speak. You got too many organics, and the microbes can only eat so much, then they get full. So there's leftover organics. So it's all really about balance. You and I have to have a balanced diet. We got to have certain things to survive. These microbes do too, so we have to tend to them. We take good care of them because they do the work for us. Activated sludge, this is our effluent compared to drinking water. You can see it's pretty clean. It's a little dingy today, and the reason is I told you that our average daily flow is 14 million gallons a day. The problem is when we have rainfall events like we had last night, and especially the ground's already saturated, we're starting to get into a wet pattern, we have a problem. Not we, everybody who runs a wastewater treatment plant has a problem of what's called I and I. Inflow and infiltration. Because you got to think about all the pipes underground out there in the counties across the metropolitan area that convey the water to the treatment plant. Those pipes are connected at joints. Those joints leak. So when you start thinking about all the pipes and all the water, rainwater that goes down into the ground, that water gets into the pipes, and what it does, it winds up increasing our flow coming into the plant. So right now, instead of treating, let's say our flow right now, Mike, would probably be 17 or 18, it might be 24, 26 coming in.
Right now it's 27.
All right, so we're close to 28. So you can see how much 1 inch of rainfall has increased our flow. Now, on a regular day, it would be almost hard to tell the difference between the two, but what happens when you get that much flow, it has a tendency to stir things up a little bit, especially in the secondary clarifiers, especially when you got one of your clarifiers out of service for maintenance, which we do now. But it's still good. It meets all the permit limits, and we're in good shape there. But golly, any questions? I need a break.
How long does it take from water in to water out?
That's a very good question. We call that detention time. What's the detention time through the plant? Well, on an average daily flow basis, I would say it's probably 14 to 16 hours from front to back. That's to make it through all of our basins. How do you figure detention time? You got to figure out the volume in each one of your tanks and what the flow rate is. And there's a formula that you work out that you could figure out the detention time. Right now, I would say with the flow coming in, I would say we're probably at 12 hours from front to end. Coming in the front at preliminary treatment, flowing out the back.
Now, go ahead.
If it were to be too much food or vice versa, how long does it take to fix it, to get it back balanced?
Another good question. All right, if you got too much food, we would increase what we call wasting. Waste activated sludge. We take some of it out. So it's just a matter of setting a valve, an actuated valve, to say we're going to waste more out of the system. And then it's an easy thing to do. So we just open that valve a little more and start taking out more. Depending on how much you let it get out of check, depends on how much you can bring it back, how long it would take to get it back into check. The problem is when you waste off too much, that is a big problem because these microbes only grow so fast. So if you waste most of your bugs out of your system, it can take a substantial amount of time to get you back on track. Then once you waste too much out of your activated sludge process, you set yourself up for other problems as well, because you can imagine the characteristics of the wastewater coming into the plant change. We got industries, restaurants, all kinds of places discharging their product, their used water, into the collection system. We got Clorox that discharges into our collection system. Clorox, bleach. Sherwin-Williams, there's some big companies out there that discharge into the collection system. So if you don't have enough bugs to do what it's supposed to do, and let's say you get what we call a slug of wastewater coming into the plant that could be toxic to those microbes, you could knock out all your microbes. Boom, they're dead. If they're dead, you're in trouble. You're not going to have any treatment. You're going to blow your permit. You're going to be in big trouble. You're going to be out of compliance. And so we don't never want that to happen, but you know, it could. So we have to take precautions. So I would rather this grow out or out of proportion a little bit, or let it grow too much than to waste out too much activated sludge. I'd rather have too much than too little.
Do you do any preliminary testing on the water coming in to make sure that doesn't happen?
Well, we're always testing what's coming in. I shouldn't say always. A lot of times we're testing what's coming in and what's going out. The permit limit, not permit limit, but the permit requires us to composite sample what's coming into the plant 5 days a week. So what is a composite sample for us? That means it's a flow proportional sample. So we got an automatic sampling device that will collect a sample ever so often. When so much flow passes by, we got it programmed to collect a sample, a flow proportional sample. So as the flow picks up, it's going to pick up more samples. As it decreases, it'll pick up less samples. But it'll pull a 100 ml sample. So 5 days a week, we're always collecting samples on the influent. And on the effluent, we're only doing 3 days a week on composite sampling. But we also have an influent pH meter, where that's really my operator's indicator that there may be a problem. Because if that pH gets below 6 or gets above 8, they have to start collecting samples. And actually the pH meter that we have up here at preliminary treatment is continuously measuring the pH. And that pH measurement is pulled back into our plant SCADA system or computer system. So as soon as it sees a 5.9, it's going to throw up an alarm on that computer system. So the operator sees it, he's going to go start collecting samples and make sure that's a true value. So he'll collect a sample, come back in here and run a lab test to see what the pH is. If it's truly below 5.9, then we're on the lookout. We start collecting other samples and making any process control changes we may need to make, and be watching out for other problems. And if that pH gets above 8, it'll do the same thing. So that's pretty much what we do. We watch that pH meter for any changes, and we do grab samples every shift. We're staffed 365 days a year, 24/7. There's always somebody here operating this plant. They look at the equipment, they collect samples, they run lab tests, they make process control adjustments. So every shift we have operational staff who are going out there collecting samples and running those tests. And that's really how they operate this plant. If they see something like the phosphorus going up, then that operator will start up the ferric feed. And then once he starts ferric feed and he's watching his alkalinity, now he's watching, well, he's always watching it, but he's really watching it. So if he's looking at his phosphorus and alkalinity, his alkalinity starts dropping off and hits below 70 or 70 or lower, he's going to start up the sodium hydroxide. So those operators are always collecting samples and making process control adjustments. And that's what keeps us in compliance and keeps us out of trouble with the state, and really what protects our environment. So thank God that we have good operators here that do a good job, because otherwise we could have some major issues.
I have a couple questions. You guys keep saying pH and alkalinity and everything. Do you monitor the hardness levels? Like, I come from New England and we had real hard water. Too much iron in the water, and so they were always having to monitor and add certain things to it to make it safe.
Right.
to even shower with.
They do that on the water side. Remember, we're wastewater, so what we do here, we're not treating any water that's being consumed by our customers in the county. We're just treating the wastewater and sending it down to the drinking water reservoirs to an acceptable level. But the water plants do that. Now, we do test conductivity, which is a measure of the salts in the water. And we got a conductivity meter right over there. We actually do that when we start having problems with our pH. So if our pH gets too low or too high, and the operators collect those samples at strategic points in the plant, they come back in here, test the pH, they run a specific conductivity, and they also measure specific conductivity, and they run COD tests. Y'all know what COD stands for, by the way? Hey, I'm full of acronyms. A lot of other stuff too.
All kind of acronyms.
COD, chemical oxygen demand, and it's just a. Did y'all say y'all knew what a BOD test was? Biochemical oxygen demand.
Yes, I did.
Yeah, and I know you know it's the measure of the oxygen requirement to stabilize the BOD flow. COD is a chemical measurement of the oxygen required to stabilize the organics in this wastewater. The thing about BOD, it's a 5-day test. So when you set up that test, you don't know what the results are for 5 days. It doesn't help us as operators a whole lot. But we could be out of compliance and don't even know it. So, but if you run a COD test, you could get that result within 2 or 3 hours. So it's a chemical oxygen demand instead of a biochemical oxygen demand. So it's a measure of the depletion of oxygen within that sample, which is very, very helpful for us.
And my other question was, you said one of your pipelines is down, your incoming pipelines, right? One of your incoming flow lines is currently down. How does that affect your daily operations?
No, I may have confused you. I'm good at doing that. We don't have any pipelines down, I hope. We have leaking pipelines.
Okay.
We do have a secondary clarifier out of service. And it's kind of related because, the rain, excess flow coming into the plant. No pipelines are down though. But we do have a secondary clarifier down. So normally we have 3 clarifiers in operation. They all have a rated treatment capacity. And when you bring one down off maintenance, that takes away from your total treatment capacity. So you're pushing more flow through 2 clarifiers. So it just kind of, like I said, it stirs things up a little more than you would like. See, if we had that 3rd clarifier online, it would handle all the flow no problems. And your water quality would even be better than what you're putting out now. But even with 2 clarifiers in service, we're well within permit limits. There's no problem. But it's just not as good as it could be if we had all 3 clarifiers in service. Because you have more treatment time, more detention time. There's more. It slows everything down a little bit. I'll explain that more when we get